It's my great pleasure to introduce our next two speakers, which are Nicolas Cerf and Leonardo Novo. And as usual, I would like to say a few things about our two speakers today. So Nicolas has done a lot of research in the realm of quantum information, quantum optics. So you see his main focus is continuous verbal systems and how to understand them from the information theoretic perspectives. He has made many, many big fundamental contributions to this field. In particular, what does it actually mean that, for instance, the quantum conditional entropy can become negative? What does it mean, or how can you clone Gaussian quantum states? How can you ensure that specific protocols are safe by distributing keys in the right way? But recently, he got also more interested in this idea of boson sampling or time-like analogs of the Hong-Ou-Mandel effect. What you need to know as well is that he actually founded the first group concerned with quantum information in Belgium. It's now 24 years ago, if I'm not totally wrong, and it's a
Correct.
great place to be at. About Leo, I think the most cool trivia about Leo is if you Google his name, you will find a teacup. Because apparently there is a teacup which has precisely this name. I don't know why, but we are not talking about the teacup today, but about the physicist
That's new information.
Leonardo Novo. In his PhD, he was a lot concerned with quantum walks and quantum simulation, and then he moved at Quick, the institute of Nicolas, and together they looked a lot at Gaussian boson sampling and the effects of indistinguishability, which leads us to our today's topic. So 2 years ago, they had a very nice paper published in Nature Photonics, which is precisely about the topic that they talk about today and led to many follow-up questions, namely, how can it actually be that boson bunching is not maximized by indistinguishable particles? We are very happy to have you, and the stage is yours.
Okay, thanks. Thank you very much, Toby, for this very kind introduction. I'm speaking in the name of both of us. So let me first share my slides, actually. So can you see them? Can you see my slide? Okay, good. Okay, so I mean, as you have heard, both Leonardo and I are going in this twin talks, going to talk about the role of particle indistinguishability in the context of quantum interferometry. And in the first part of the talk, I'll be talking about one specific feature which we have discovered a few years ago, which we now call anomalous boson-bunching. And as Toby just explained, you will see that this is a very unexpected feature of quantum interferometry. So, so my talk, so the first part of the seminar, so my talk will be based on two papers. The first paper was published now 2 years ago, and it's co-authored by Benoît Seron, who you can see here, and Leonardo, who has been nicely introduced. So the second paper, if I have some time left, otherwise this will be for the questions. The second paper is a follow-up paper where Leo Pioge also joined the group, and we made some further progress on this question. So the general context of our work is boson sampling. So as you probably all know, there's been a lot of excitement for the last 15 years about the idea that sampling the output distributions, if you have a large-scale interferometer and if you inject single photons at the input of it, so sampling the output distribution is a hard computational task. So I won't enter into the details of why is it a difficult task, but I mean, as you know, this is a possible way to demonstrate experimentally the quantum advantage for a specific computational task. So this won't be the topic of my talk. Basically, the idea here is just to say that this is an incentive for a better understanding of quantum interferences in large-scale interferometers, basically. So we would like to understand the basics of quantum interference, and we have focused on one particular thing, which is boson-bunching. So I'll first spend a few minutes recalling you, I guess most of you know about this, but recalling the Hong-Ou-Mandel effect, which is the paradigm of two-photon interference. So this is also a textbook example where you can really see the complementary principle which is at play. Because you may compare the situation where you have perfectly distinguishable or perfectly indistinguishable photons, and see what follows from this distinguishability. So if you consider first the ideal case where you send two photons and those photons are fully indistinguishable, you send them at a 50-50 beam splitter, then since they are indistinguishable, quantum mechanics tells us that they will behave as waves. Therefore, we will have interferences, and it so happens, and it's well known, that there will be a destructive interference between the scenario where they both cross the beam splitter and the scenario where they are both reflected, which means that eventually there will never be any event where we have a double click, a click at this output port and another click in coincidence at the other output port. So there will never be any coincidence. That's the Hong-Ou-Mandel effect. So just the opposite situation, if you now consider that the photons are distinguishable. For instance, they could have different colors, different wavelengths, or they could have orthogonal polarization, or they could arrive at different times. So if by any means you may fully distinguish the two photons in the same optical setup, then they will behave just like classical balls, which means that each ball will have a probability 50% of crossing the beam splitter and a probability 50% of being reflected. So now we will have four equally probable possibilities here, which means that with probability 1/2, one of these two middle possibilities will occur. So we will actually see coincidences between the two detectors that are put here and there. So this is because the photons behave now as just as particles. Of course, these are very extreme cases, and in between we have the more interesting situation where we have a partial overlap between the two photons. And the general situation that is described is the situation where we have two wave packets and they partly overlap because of the different timing. And then you may look at the probability of a coincidence as a function of the time difference here, and you find the famous Hong-Ou-Mandel dip, right? So in the middle here, this is the situation where the two photons are completely indistinguishable. So all this is very well known, and the math behind this is quite simple. One may just express the probability for coincidence as a function of the overlap between the internal state of the two photons. So this could, for instance, be the polarization state of the two photons. So depending on the overlap between the two states here, you will have a smaller or larger probability of coincidence. And from this simple formula, you see, of course, that if they are perfectly indistinguishable, the overlap is 1, and therefore the probability of coincidence will be 0, as I just told you. If they are completely distinguishable, if they are just like classical balls, then we will have a probability of coincidence equal to 1/2. So all this is quite well known. So now in the rest of this talk, I'll be considering the question of how can we generalize this for more photons and more modes. So there are many ways of doing this generalization. We have focused on one possible way to do it, which is to consider an arbitrary linear interferometer, which can be described as a unitary matrix, an arbitrary unitary matrix acting on the mode operators. And we feed this interferometer precisely with one photon per input mode. That's just one possible generalization of the Hong-Ou-Mandel effect. And the question is, what is the probability that all photons bunch into the first output mode? Of course, we consider the first just arbitrarily, it could be any other one, but we consider the first output mode, and we look at the probability to find all our photons here. So this probability is, of course, expressed by this squared overlap here. So we take the input state, we process it through the unitary, and we close this overlap with the situation where we have an n photon Fock state here. So this is again very well known. if the photons are all distinguishable, this probability will simply be a product of these squared unitary matrix elements. So basically just a product of the probabilities that each of these photons end up here. And it's also very, very well known that in the other extreme case, if they are all perfectly indistinguishable, if they are ideal bosons, then there will be this famous n factorial prefactor here, which is a signature of the fact that these are bosonic particles. Of course, we are interested in the situation where we are in between these two extreme cases. So when we have partially distinguishable photons. So this was first studied by Maltetici like 10 years ago. So he considered the following scheme where he considered n photons again sent into this interferometer, but now the input states of these photons are arbitrary, so they are described by state vectors phi1, phi2 up to phi n. And at the end, what matters is the matrix which is formed by all pairwise overlaps. So this is the Gram matrix. This matrix is called S, and it's often called the distinguishability matrix because it encapsulates basically the distinguishability or indistinguishability that we have among all these within this collection of input states. And again, Maltetici was looking at the probability of having all these photons detected here in one single output mode. And interestingly enough, what we have here instead of n factorial is the permanent of this S matrix, the permanent of this matrix, which is describing the distinguishability of the photons. So the permanent, as for those of you who don't know, the permanent is an object which is very similar to the determinant of a matrix, except that we get rid of the alternating signs plus or minus signs. So it has the same expression as the determinant, except that we do not have this plus or minus signs here in front. So interestingly enough, S, I didn't say it, but S is a positive semi-definite matrix, and it can be shown that the permanent of a matrix, of a positive semi-definite matrix, is lower bounded by 1, upper bounded by n factorial, and this precisely corresponds to the two situations that I've considered. Either they are all fully indistinguishable, in which case this will be factorial of n, or they are all fully distinguishable, in which case this permanent will be 1. So all this to say that there is nothing very unexpected here. It really behaves exactly like the Hong-Ou-Mandel effect, and this probability of single mode bunching will be maximum in the case all photons there are fully indistinguishable. Okay, so nothing really unexpected. So first, let me go to a next generalization. That will be the last one. I would like to generalize this still a little bit by considering not one single output mode here, but a small subset of output modes here. And I'd like to consider what we call multimode bunching. So this was actually first studied by Cecenovic. So we would like to look at what is the probability that the photons that we send, again, n photons with these internal states, what is the probability that these photons end up all in this subset of output modes? I mean, that's the question that we may ask, of course. And the answer to this question, as given by Cecenovic, is again given by a permanent, but this time it is the permanent of the Hadamard product. So the Hadamard product is an element-wise product. The Hadamard product of this distinguishability matrix S, depending on the input states, and another matrix H, which is defined here. And all you need to remember is that this other matrix H, it depends on the interferometer, and it depends on the subset of output modes. So basically, we have to compute this permanent of this Hadamard product to know what is the probability. So from everything I've said up to now, it's of course very natural to assume that, again, the probability for multimode bunching will be maximum in the ideal case where all photons are completely indistinguishable, right? I mean, this really makes a lot of sense. And this is actually something which was conjectured by Cecenovic. And this is something which is true in the case we only consider one output mode. At least in this case, we know for sure this is true. So mathematically, this would translate into the fact that the permanent of this Hadamard product here is upper bounded by the permanent of H alone. This would be the case of the ideal boson case, the case where all photons are fully indistinguishable, because in that case, the S matrix, remember this is a matrix with all overlaps, this matrix would be filled with ones. So this Hadamard product disappears and is just a permanent of H, right? So if this inequality here is actually just a way of mathematically expressing the fact that the bunching probability is maximum if all photons are completely indistinguishable, which, as I said, is very natural to conjecture. And there are several reasons why it is plausible, but probably the main original reason to conjecture this was to rely on an old conjecture on matrix permanence. As you can see, this was conjectured 40 years ago, more than 40 years ago. This conjecture by Papat and Sunder is that if you take any two positive semi-definite matrices, A and B, the permanent of the Hadamard product will be upper bounded by this expression. And if you plug in for A here, you plug in this H matrix that I described before, and for B, you plug in the distinguishability matrix, this translates into this inequality that I've already written before. So this translates precisely into the multimode bunching conjecture, right? So the multimode bunching conjecture, it is just an immediate consequence of this Papat-Sunder conjecture. And perhaps even another reason why it's very plausible that this should hold is the opposite situation for fermions. For fermions, we can basically make the same type of calculations, same type of reasonings, except that permanents are replaced by determinants, and the direction of the inequalities is flipped, so the inequality is in the other direction. But basically, what is important here is that this inequality is actually proven. It was proven like almost a century ago. So this means that in the case of fermionic multimode anti-bunching, it is actually the case, and it was proven, it is the case that the probability for n fermions to bunch into some subset of output modes is this time minimum in the case the fermions are fully indistinguishable. So all these elements really seem to indicate that something similar has to exist for bosons, but as you may guess, I wouldn't be given this talk if it was the case. So our work started because we, almost by accident, we found out that there was this paper, a paper by Stephen Drury, in some mathematical journal, which has remained basically unnoticed, at least to the quantum optics community. There was one paper published now 9 years ago, which simply showed that this conjecture is wrong. This paper, the abstract of this paper, I read it, it's a counterexample to a question of Papat and Sunder is presented. So the paper basically exhibited this matrix. It was a very short paper, 1.5 pages. It didn't give any reason why this conjecture is violated, just showed us that there is a way to violate this conjecture. So of course it triggered our curiosity, and of course we wanted to know whether this implies something in quantum optics. Of course, I don't have the time to give you all the steps in our reasoning, so I immediately jump to the result. So the result is that yes, this counterexample can be translated into something meaningful in quantum optics. It translates into one particular interferometer and one particular input state, for which we have something very weird happening with multimode bunching. So let me explain in a bit more details. So we have here, first of all, this matrix, I didn't say it, it's a 7x7 matrix, right? So this translates into the fact that we are dealing here with a system with 7 photons, and we have actually 7 photons in a 7-mode linear interferometer. So the five first photons, they enter a Fourier interferometer here, and the last 2, they enter 2 beam splitters here that you can see here. So the 7 input photons are those 5, this one and that one. And we are looking at 2-mode bunching. So the bunching of all of 7 photons impinging either here, being detected either here or there. So I don't really give you the reason, but it so happens that it is enough to consider a 2-dimensional Hilbert space for the internal states of the photons in order to show this counterexample. So a very natural physical implementation would be the polarization of the photons, which is why we explain this counterexample with polarization. So we assume that 7 photons are impinging into this interferometer, those 5 plus those 2, and their polarization state is actually shown in the Bloch sphere here. So you see that we have here 5 black arrows here, which correspond to 5 equally spaced polarization states along the equator of the Bloch sphere. And then, in addition, we have a vertically polarized and horizontally polarized state. So the north and the south pole and the Bloch sphere. So these are our 7 polarization states. We call it a star-shaped polarization pattern. And what is particularly interesting is that if we compare the probability of all our 7 photons to bunch onto these 2 output modes, if you compare it in the situation where they are all indistinguishable, so we call it bosonic, ideal bosonic case, to the probability when they are occupying this very specific polarization pattern, very unexpectedly, we see that the situation where they occupy this star-shaped polarization pattern gives rise to a slightly higher probability of bunching. So the probability for 7 photons to bunch here is slightly larger if the photons are partly distinguishable, which is very weird, very unexpected, compared to the case where they are all in the same polarization state. And as you can see, the violation is of the order of 7%, which isn't very large, but it's also something which might hopefully at some point be experimentally verifiable, accessible. So let me just say that now that we have something, now that we have a quantum optics circuit, it's of course very tempting and very easy to generalize it. And a very simple thing to do is to generalize the 5-mode Fourier transform with an n-mode Fourier transform. And this can be done. We just have to change a little bit the circuit. And the interesting result is that the probability, the violation ratio here is now probably of order of n. So this means that we can arbitrarily increase the violation ratio here by increasing the size of the circuit, by considering more and more photons. Because you should keep in mind that both the numerator and the denominator decay exponentially with n. So I don't claim that it's easy to measure this violation ratio experimentally, but in principle, we know that the ratio is increasing with n. And another thing which is worth saying is that now that we have a quantum optical circuit, we may now look for a mechanism, try to understand where it comes from. While from the math perspective, it was just something which was observed with no explanations. So we have found out one way of understanding how it works. I won't explain it here in details. Let me simply say that the explanation is connected to the state that we have here in the middle, the state that we have here after the Fourier interferometer. So if, as a benchmark, I consider the situation where all photons are all the same here, then it is actually known that the state that is here will be a known state, so n0 plus 0n state, which means that, for instance, let's focus on the n0 component. When we have n photons here and 0 photon there, so we have n photons here plus 1 photon there. If we focus on the occurrence of n plus 1 photon here, if you do the math, there will be the n plus 1 factorial term here, because we want the n photons here plus 1 photon here to glue together and give an n plus 1 Fock state here. So that's the reference case, or the benchmark, let's say. But if you compare to the situation where we use here this star-shaped polarization pattern here, the state that we have here, it's more difficult to write it, but we have, analyzed, let's say, the leading term. It's not exactly the leading term, but like the main term of this state here. And it so happens that it is just a Fock state with n photons, but n photons occupying a mode which is delocalized, a mode which is spatial polarization delocalized mode. So it's a little complicated to explain with words. But if we do the same rotation in the mode space for those 2 photons, we have the Hong-Ou-Mandel effect. And basically, at the end, we have n photons here and 2 photons there. Therefore, we have an n plus 2 factorial term appearing. And this is what leads to anomalous bunching. So here you actually see the violation ratio as a function of the number of photons. So in blue here, you see the actual curve. Actually, we can compute this up to a little more than 20. So you should keep in mind, I didn't say it, but computing the permanent is exponentially hard. So we can go very far, unlike we could do for determinants. But nevertheless, you see in this curve here that it's more or less a linear behavior as we expected. And you also see that apparently with this type of schemes, at least the first dimension with which we have a violation is n equal to 7. So at least with this family of schemes, we know that we need 7 photons in the 7-mode interferometer in order to see something unexpected. Yeah, perhaps this I will skip. And actually, I will just show you this, and then I guess I will skip the second paper because I don't know how much time do I have left, Toby.
Around 0.
Okay, so
but you can do 1 or 2 more slides.
Okay, perfect. So let me perhaps just introduce what is the content of the second paper with this slide. So in this slide here, I'm presenting what we call the landscape of distinguishability matrices. So we are actually considering convex mixtures of 3 distinguishability matrices, namely this one here, which is the matrix filled in with 1s, so the case of the ideal case of indistinguishable bosons. This one here, which is the case of fully distinguishable bosons, just like classical balls. And this point here, which is what we call this star state, right? This state which gives rise to this anomalous bunching. And what we show here in this ternary diagram is the violation ratio, or more precisely, the logarithm of the violation ratio. So here the violation ratio is 1, of course, so the log is 0. And if you follow this line here, it gently decreases towards the case of classically distinguishable bosons. But the interesting thing that we can see on this diagram is that if you go from the ideal case to this anomalous bunching instance, the ratio first goes down and then goes up again. So somehow you could think of this anomalous bunching instance as kind of an isolated island in the landscape of distinguishability matrices, not at all something that you have near the ideal bosonic case. So this leaves open the possibility for a weaker conjecture, which is the object of the second paper, which I won't present. But this weaker conjecture is that, okay, we now know that the ideal case of indistinguishable bosons is not the maximum, it's not the global maximum that we may reach. Nevertheless, it may still be a local maximum, meaning that if we slightly perturb the polarization, for instance, of photons, starting from a situation where they all have the exact same polarization, it is very natural to assume that the bunching probability can only go down. So at least in the neighborhood of this ideal point here, the bunching probability should go down, so it should be a local maximum. So as you may guess, this is also wrong, but this is the object, this is the topic of the second paper. And let me now just show you the conclusion. Yes, so as a conclusion, let me simply say that this is just the beginning of a long way, and there are still many open questions. So for instance, we would like to know whether other counterexamples could be found, in particular simpler schemes. We don't even know whether it is or not possible to find a scheme with less than 7 photons, yet a scheme where we could observe anomalous bunching. Or could we find stronger violation? I mean, we know we can have large violations, but for impractical optical circuit with many photons. But could it be that we can have a large violation with only a small number of photons? This we don't know. We also would like to know how this could be applied, for instance, to the validation of boson sampling experiments. And also, let me simply say that there are plenty of conjectures, not plenty, but there is a collection of conjectures. Some of them are still open, conjectures on matrix permanence. The permanence are not very well understood objects. Probably the most famous of them is the Leib's permanent dominance conjecture. So it's of course very tempting to analyze the link, the consequence of these in quantum optics, or more generally to analyze the connection between, I mean, this shows that there is a very deep connection between matrix permanence, which belongs to mathematics, basically to linear algebra on the one hand, and many photon interferometry on the other hand. So I think this is a very fruitful interface. So here you see again the references to the 2 papers that I've been presenting the first, but you may want to hear about the second. Thank you very much.
Nice. Thanks a lot. Okay. So before Leonardo takes over, we have now some time for questions to Nicolas. Just unmute yourself, raise the hand, however you like. So maybe let me start with a question. I don't know why I didn't have this question before, but after listening to your talk now, you said in between that for fermions, the situation is opposite. They're
Yes.
also, so first of all, that you get a minimum instead of a maximum, but also that you basically indeed have the minimum even for many output modes, right?
Yes.
Exactly. So what I was just wondering is that where is the turning point? Because of course, we know that in between you can have something like anionic statistics. Is there anything known about the bunching of anions? Do you know anything in this direction?
I mean, there are papers talking about immanence, which is an object which isn't permanent or determinate. But about anions, I don't know. I doubt there is something like this, an analog to this inequality, but I am actually, I should confess that I don't know. I don't know if Leonardo knows anything about this, but
no, yeah, it's not clear what kind of object appears when you deal with onions, right? Like assuming let's say a billion onions. I don't know what's the mathematical object to appear which is not determinant or permanent. Yeah.
But Ernesto has been, I mean,
Yeah, I don't know if
Ernesto
Ernesto is attending us, so I don't know if he. Yeah, I don't think he.
Hi. No, I don't have anything much to say about that.
Okay.
Okay.
So if you don't have anything to say,
yeah,
then
so it's an open question.
I mean, that's also good, yeah. I just wanted to bring it up, and that's fine.
And I mean, here we are talking about what would replace the permanent or the determinant. But what I was saying that even if this was known, this is even one step further, right? Finding an analog to this inequality with an object which wouldn't be. This is even one further step. I don't think there is anything like this. Not that I know of. Not that I know of.
Yeah, I mean, the determinant basically has half mixed signs. The permanent has the same signs, so anions will probably have a lot of phases instead of just plus or minus. So some weird object when you sum over the elements, but I don't know. But okay.
Yeah. I have a question, if I may.
Yes, please go ahead.
So I was wondering about this very symmetrical set of states that you use on the equator, the Bloch sphere, and then the North Pole, the South Pole, right? So this reminds me of some settings for violations of specific Bell inequalities. So I was wondering if there is some connection of the directions you have to prepare the states in, and the settings that you need in order to violate some specific Bell inequality, maybe Gisin's elegant inequality or something like that.
Okay. I've never thought about this connection. But for me, Bell inequalities is also always in a bipartite setting, right? Here, I don't even see very clearly where is Bob, where are Alice and Bob. I mean, that's probably an interesting. I mean, if you know of a scheme where they are also using the Bloch sphere in a similar way, that would be exciting to look at. But
I see. Okay. Yeah, because what I had in mind is you can start with a maximally entangled state and use the settings at Alice and Bob, right? Or you could do the reverse thing and prepare separable states and then project them onto Bell pairs. So the probabilities are the same, but you may be able to make a connection of the settings with the directions, these states that you have. But I don't have anything concrete in mind, but maybe I can discuss this later. We can discuss.
Yeah. I mean, there was any connection with non-locality. I think there has never been a paper about any connection between this world of indistinguishable or partly distinguishable photons and Bell inequalities, isn't it? So that would be nice.
Okay.
There is a related question in the chat. I think it has been partly answered, but I will nevertheless read it. It's from Maciek. Any intuition on what the importance of the star pattern is?
Unfortunately, not much. I mean, and perhaps I could just come back again to this to the interpretation of the mechanism that we have. I mean, this can be done analytically. We can actually really look at this Fourier interferometer. It has a very nice, very symmetric structure, and we can also feed it with a nice structure of polarization state, which are along the equator. So we see that what happens in the Fourier interferometer is such that the dominant term here is just one single Fock state. I mean, we could not really prove that it is the dominant term, but at least it's the term that plays a role here. Somehow, I think it's very strong result that because we have n photons at the input, which are all occupying different modes, and we end up with at least some component where all photons are occupying one single mode. It just so happens that this mode is a delocalized mode. So there is a conspiration of the phases. If you do the calculation, obviously there is a connection between these phases along the equator and the phases that occur in the Fourier interferometer. I mean, it's not a very deep understanding, but I cannot really say much more than the fact that we have phases here which resembles the phases that occur in the Fourier interferometer, and all this gives rise to this nice effect. But this is not very deep, and that's probably the reason why we don't know of other counterexamples. It would be nice to find many counterexamples, but we don't have really much imagination. So basically, we start from this example, which simply comes from this paper by Drury, which we simply translate into a quantum optical interferometer. Yeah, so.
Okay, so you got a thank you via the chat. So I think it's time to move on. Let's thank Nicola again.
Thank you.
And now it's time for Leonardo. Please share your screen.
Hi. Yes. Oops, not the right down. Just 1 second, please. Okay, so share screen 2. Can you see it?
Yes, this looks good.
Okay, I'm gonna put it on full screen. Okay, I think you can see full screen, right?
Yes.
Okay, great. Yeah, so thank you, Toby, for the invitation and introduction. So yeah, let me get to the part 2 of this talk. So usually this talk is the second part of the talk is experimental. I'm not an experimentalist, but I will talk about some experiments that have sort of a similar inspiration to understand boson-bunching with the partial distinguishable photons. But okay, maybe just to bridge with the talk of Nicola. So Nicola was explaining this counterintuitive effect where we have a particular state of partial distinguishable particles that end up bunching more in a particular subset than if I had fully indistinguishable particles based on this connection to matrix to a conjectural matrix permanence. Then there are many related questions that Nicola didn't have time to address, and neither I will address, but just to complete sort of this bridge. Yeah, so at the end of Nicolas's talk, he was mentioning this new work, I mean, from a couple of years ago, where we asked we tried to analyze if this multi-mode bunching conjecture is true in a setting where we're almost indistinguishable boson. So here we do a slight perturbation of a state of equal, photons in an equal internal degree of freedom. And the interesting thing here is that we found a connection to another mathematical conjecture that didn't have a physical interpretation, as far as we knew. And there was also a counterexample to that other mathematical conjecture, also found by Drury. And so from translating that counterexample, we could also show that even perturbing slightly the states of indistinguishable particle can actually lead to this anomalous bunching effect, which means that this is not, let's say, universal way to validate boson sampling experiments, even if you are in a regime that is close to indistinguishable photons, right? And then even more recently, we tried to look at, let's say, more physically motivated uh, models of partial distinguishability. So you could imagine that, okay, ideally I'd like to have the same state, but maybe because of misalignment, there are some time delays when the photons arrive. So you can consider perturbation to, let's say, a wave package that is perfectly synchronized. You consider perturbation that's a small time delay. And so if we consider this particular model of partial distinguishability, what we questioned was, okay, is now the multimode bunching conjecture true? And the answer is still no. And this was a numerical counterexample found by Leo and Camille, who was a master student at ULB, supervised by Nicola. And so it seems that, yeah, even if we restrict to certain physically motivated models of partial distinguishability, this is not a universal effect. There's still, like, this anomalous bunching can still happen in some dimensions. There's another very interesting work, which is not by neither me or Nicola. So it's actually, they consider a model where they have identical density matrices for each input. And they again asked the similar question whether multimode bunching is true. So that whether this probability of seeing all the photons in any subset is maximized by indistinguishable particles. And here they actually managed to make a connection with this Leaves permanental dominance conjecture, which is this open conjecture that Nicola briefly mentioned. This is a work by Geller and Neal. So if this conjecture turns out to be true, then this multimode bunching conjecture is true for this particular model, which I don't have here, but it's basically the same role everywhere, same mixed state at the input of boson samplers. Okay, so this is just a little bit of what's going on in this direction. But now I'm going to shift to another direction, which is still related. But basically, the question is a little bit different. We're not looking at whether bunching is maximized by indistinguishable particles, but we're trying to understand what happens in the middle, right? When we start, and also we're trying to see something that we can observe with current setups. We have to go to a smaller number of photons. So the question we ask is a bit different. So basically, we want to understand the behavior of full bunching in a simple system. Let's say it's the simplest system after the usual Hong-Ou-Mandel test with 2 photons. So let's go just to 3 photons. And let's try to understand how the full bunching in a given mode behaves with partial distinguishability, okay? And so in particular, we're interested in analyzing what happens when we compare 2 situations. Let's say in the first situation, we have some initial states psi I with some polarization and maybe some wave packet profile, some time delay. And now we go to another setting, some psi prime I, and in this new setting, we have higher pairwise overlaps, okay? So what this means is that if I did just pairwise Hong-Ou-Mandel tests between this new set of states, describing the individual photons, I would see higher Hong-Ou-Mandel visibility. So I would say, okay, pairwise, my photons are more indistinguishable. But does this mean that the full bunching here would also be higher? Because again, ideally, well, we believe that, okay, the more indistinguishable, the more the photons would bunch. But we'll see that it's a little bit more complicated than that, because there are these sort of genuine 3-photon effects that appear, and they have physical implications. And so basically, these pairwise Hong-Ou-Mandel visibilities are not enough to describe what happens in a three-photon scenario. Okay, this is and this was the result of this paper, where there's also an experiment with INL, including Ernesto Galvão, who was attending the talk, and the University of Sapienza and CNR in Milano, who were doing the experiments and creating the photonic chips. All right, so first of all, okay, we need a setup that allows us to manipulate this partial distinguishability between the photons. So Nicola already introduced this Gram matrix, which is the matrix of overlaps. So we know that any outcome probability here can be described in terms of the elements of the linear interferometer, so this 3x3 matrix, and unitary matrix, right? And this Gram matrix of the overlaps of the wave function, okay? And there is a, for three photons, you can choose, you have some gauge freedom in choosing this parameterization of this Gram matrix. If you're interested in this, I recommend this paper, also where Ernesto is involved, Misha Osmaniak and Daniel Broad. And so we pick a certain gauge choice for the parameterizing the Gram matrix for three photons. These are the usual Gram Hong-Ou-Mandel visibilities, so the overlap squares. But then you realize that the most general Gram matrix, even up to gauge choice, has this funny phase that appears here, and that has physical consequences, as we'll see later. But before, let me just quickly talk about the experiment. So I won't be able to answer tough mental questions, but I'll just give you a little bit what the setup is. So we have a quantum dot source that's able to generate trains of photons that have quite high indistinguishability. Then we have to demultiplex them to sort of convert this sort of time bin photons to different spatial modes. And here, so this is the multiplexing part. And here there are some wave plates that allow us to rotate polarization. So here there are two wave plates. So there's some partial control of polarization on a given, let's say equator of the box here, for example. And here we have full control by three different wave plates that allow us to control three different angles. So in principle, here you can manipulate the full manipulation of the polarization of the photon, of the third photon. And there's also an extra time delay. And it turns out that this setup is enough to prepare any kind of Gram matrix of three photons. Okay. Then these three photons with this prepared internal degrees of freedom are sent to an interferometer, 3x3 interferometer, which ideally would like to have photon number resolving detectors here. But since these are, are expensive or not so easily available, then there's this demultiplexing scheme to have a pseudo photon number resolution. Okay. So at the theoretical level, we have a setup that allows us to control this Gram matrix and do photon number resolution, even though in practice is implemented by this sort of cascaded scheme. Okay. So let's say these are the playground. And now we can try to understand what happens to these full bunching probabilities as a function of partial distinguishability in different scenarios. And so I'd like to define these two quantities that are going to be important for what comes next. So one of them is this average Hong-Ou-Mandel visibility. So it's the average pairwise overlaps between the three photons. Okay. And this quantity, which is interesting, which is sort of really a genuine three photon quantity or three particle quantity, which is often called a Bargman invariant. So if you check this paper, yeah, because it's an invariant under basis change of this, the description of these three states. So if I do the same unitary on the internal degrees of freedom here, here, and here, this quantity doesn't change, this quantity doesn't change. And the interesting thing about this quantity is that it's complex. And so it has this phase that appears here in the Gram matrix that has physical consequences because we cannot remove it by a gauge transformation. And this is sometimes called a collective photonic phase. For three photons, it's called a triad phase. There's been experiments, for example, by Walmsley group measuring this phase in some other setups. There's also a theory paper by Chesnovich and Becerra. And so here, okay, we're interested in focusing on the full bunching probability and how it depends on these quantities. So Nicola already showed this expression to use. So this you can interpret it as the classical probability as if the particles were fully distinguishable. So this would be what would happen if you had a normal stochastic process where, you know, the probability of going from 1 to 1 would be given by this, the from 2 to 1 would be given by this, and so on. So independent classical balls, let's say, going to the same place. But then there's this boosting factor permanent of S that Nicola mentioned. And if you actually compute the permanent of S for 3 particles, you can express it in terms of this average moment of visibilities and the real part of the Bargman invariant, okay? Which is what appears here. So you see this cosine of this phase. And so indeed, you can see that if I now increase my Hong-Ou-Mandel visibilities alone, then this has a positive enhancement factor. But there is this thing that can be manipulated independent. There's this third parameter, which is this collective photonic phase, that also plays a role and can even turn this term to be negative. And by the way, we know exactly in which, what kind of complex numbers are allowed for this phase. So this is sort of the range of numbers in complex space that is allowed by quantum mechanics for 3 wave functions. So this is characterized in this paper, and there's been some follow-up works for higher order Bargman invariants, but I'm not going to talk about this here. And so this is consequence. The fact that this is restricted in this set of complex numbers also has consequences in terms of what kind of bunching probabilities can be observed. And so the experiment that the people in Sapienza, Rome, with the chips from CNR did was to manipulate these Hong-Ou-Mandel visibilities and the collective photonic phase by playing with polarization and time delays. So here we see the results of when the collective phase is 0 and we increase the average Hong-Ou-Mandel visibilities, we see an increase of the full bunching probabilities. But then at some point, we can continue increasing the average Hong-Ou-Mandel, visibilities, and at the same time manipulate the phase. And because the phase has a negative effect here, as you see here, because of this cosine, so in particular, this is minimized when the phase is pi, then we see that even if we keep increasing the average pairwise Hong-Ou-Mandel visibilities, the full bunching probability can decrease. Okay, so there's this effect of this triad phase. And here is just the same plot, but with a different metric, which is the absolute value squared of the Bargman invariance. So we can, which is basically the product of the pairwise Hong-Ou-Mandel visibilities. And here again, we see that we increase it, but at some point, if you manipulate the phase, even if you keep on increasing this, the full bunching probability is going to decrease. So this is sort of the counterintuitive effect that basically tells you, okay, we have genuine 3 particle, the relation between the wave function of all the 3 particles plays a role, and not just a pairwise. So this is another, I don't know how much time I have, so I can go either quicker or, do you know, Toby?
It's fine. You can still do
Okay,
5 to 10 minutes.
Okay. So we also analyze other notions of bunching. So what I've been talking about up to now is this full bunching probability. So basically, I was concerned about these events 300, 030, 003, events of this type. But now you can define a more, let's say, a wider notion of bunching, which is, okay, I'm saying that the particles bunch as long as there is at least 2 photons in a given mode. So either 2 or 3 photons. So I'm calling this set of events the bunching events. And so I can also try to analyze how this behaves with partial distinguishability. And now we don't have, it's a little bit more complicated because we don't have this sort of factorization that appears here. So for full bunching, there's a contribution of the interferometer times a contribution of the Gram matrix, okay? If now I consider these bunching probabilities, there's actually an interplay between the two, so you cannot separate them easily. So meaning that these statements are sort of interferometer dependent. But one interesting interferometer is the balance treater, which is sort of the unbiased beam splitter, but for 3, right? So you have a balance treater, which is also like the Fourier transform for the 3. And there you can compute these bunching probabilities and this full bunching probability. So the full bunching I already mentioned before, but now I'm summing all these 3 possibilities for this balanced treater. And but now I'm also computing the bunching probabilities. And naively would think, okay, the more bunching, the more full bunching would also have the more bunching, right? Just because, well, bunching also includes the full bunching events, right? But if you notice, there is a difference in sign in the contribution of the phase here. So here you have cosine of phi. So here, if you want to maximize full bunching, you have to put this phase to 0. Whereas here, if you want to maximize bunching, you have to put this phase to pi. So they have very different behaviors, which is also, again, a little bit counterintuitive until we do the calculations. It's maybe even more counterintuitive because this quantity here, as Nicola was saying, is maximized by indistinguishable bosons, but the bunching probability is minimized by indistinguishable bosons. And the reason is that there are some suppressions due to the treater, due to some symmetries of the treater, and there are some suppression laws for the treater. There's an old paper by Buchleitner, Tichy, and other people explaining the suppression laws. And actually, this all these events, if in the ideal case, they are suppressed um, for the treater if you have indistinguishable bosons. So it is funny that indeed for the balanced treater, the indistinguishable boson minimize the bunching probabilities, even though the full bunching probability is maximized by indistinguishable boson. And so one could ask, okay, what is the state that maximizes the bunching probability? And this is actually a state that has, well, maybe I go to the next slide. So it's a state that when you compute the Bargman invariant, this quantity here that I mentioned before, the phase is pi, so this is negative, so it has the maximum negativity of this, and also the maximum collective photonic phase of pi. And so to realize the state, we actually need to put the average Hong-Ou-Mandel visibilities to 1/4 because of these constraints between the norm of the Bargman invariant and the phase, which is basically what this border tells you. By the way, this was for 4, so I'm asking you to ignore the other thing. This is for Bargman invariant of order 4 that I'm not mentioning here. But okay, I'm talking about the blue curve. So yeah, so this was also observed experimentally. So the experimentalists in Rome, they manipulated the state preparation such that the average Hong-Ou-Mandel visibility stay around 1/4. So here you can see that they are all about 0, all the pairwise Hong-Ou-Mandel visibilities are about this value. And then they independently tune this phase by playing around with polarization time delays. And you see that the full bunching probability is maximized when this phase is at 0, as I mentioned before. But the bunching probability is minimized when the phase is 0. And it's actually, this one is minimized at pi, and this one is maximized at pi. All right. Yeah, so basically, in terms of the space of allowed complex number for this Bargman invariant, we're sort of doing this trajectory here, which is a trajectory of radius 1/8, and yeah, you have full freedom of choosing the phase. Because in other places, sometimes you don't have full freedom of choosing the phase for a given absolute value of this quantity. Maybe one last thing that is quite related. Also, this is another paper, but I wanted to mention this result briefly just because it's very related. So if you look at the probability of free photons bunching for partially distinguishable particles, you have this expression that we already mentioned. For distinguishable particles, this permanent of S turns out to be 1. And so you have basically the classical behavior, if these were independent classical balls. And so now if you notice, okay, this is very simple to, if you take the ratio of these two, because of this factorization I was telling you about, then the ratio only depends on the partial distinguishability of the input state. So it does not depend on the interferometer. So even if you don't trust the implementation of your interferometer, you can still use this ratio to certify that your particles have a high degree of indistinguishability. So somehow you can have access to permanent of S, which you can see as a quantifier of bosonic indistinguishability, also in a very mathematical sense. So if you refer to this paper, I won't have time to talk about it. But basically, yeah, so you can use this quantity to sort of measure how indistinguishable your particles are in a way that's interferometer independent. You just need to do the experiment with distinguishable photons. That's very easy. You just send one photon at a time. And then you do your experiment with your three best photons in some sense. And then you take this ratio and you get access to this. And this, so here in this plot, we see for a distribution of random interferometers, the ratio of these two quantities, and we see that it's interferometer independent. I mean, up to some experimental errors, of course. And yeah, so the ideal value for three photons is 3 factorial, which is 6. But of course, also due to imperfect photonic indistinguishability at the level of the sources, here we see a value of 5. Okay. And this is one of the results in this paper. We also talk about other ways to sort of get guarantees on multiphoton indistinguishability that do not trust the correct implementation of the interferometer, which is important because sometimes, yeah, there's errors in the implementation, or you can have access from data coming, I don't know, from, for example, Quandel devices or other online devices that you don't even have access to the experiment. So this is one of the motivations of this paper, to have a sort of guarantees on indistinguishability, do not trust so much the interferometer implementation. So this was also done in collaboration with our colleagues in Rome and CNR Milan. Okay, so maybe I'll just go to the summary. So this is more like the summary of Nicolas's talk. So multimode boson-bunching is not always maximized when particles are indistinguishable. And there's this very interesting connection with mathematical conjectures on matrix permanence. But now, even if we go like to 3 photons, there are already some non-trivial effects happening. And basically, one of the main things is that full bunching probabilities do not decrease monotonically with the pairwise Hong-Ou-Mandel visibilities. The collective phases play a role. There was an experimental observation in the 3-photon experiment. And also that full bunching events gives access to measures of indistinguishability without trusting the implementation of the interferometer. And just a little bit of advertisement. This is the group at INL. So Ernesto Galvão was also involved in these experimental works that I mentioned. Benoit Seron, you already saw him before. He was involved in the Nature Photonics paper that Nicolas was talking about. Now he's a postdoc here. And these are some of our projects. And yeah, this is a picture of the group and some of our collaborators involved in these works. And thanks a lot.
Thanks a lot, Leonardo. Oh, that's actually really interesting what you were able to achieve experimentally already. So we have time for questions to Leonardo or simply generally to this beautiful topics. Just unmute yourself and ask. I'm sorry because I have to start actually, because there's one thing I really want to understand better. So you said that you want to use this also as a type of certification method. And one thing I was wondering about is, what is the role played by loss and crosstalk and all the stuff that you usually have in photonic chips?
Yeah, so loss is a big problem, but usually what experimentalists do is just they post-select on the 3 photons, making it to the end of the chip. So this post-selection sort of corrects for loss. It's a little bit more tricky than that because actually the G2 of the photons you're sending is not exactly ideal. So there's sometimes you think you're sending a single photon, but there's a small probability that you're actually sending 2 photons in a given mode. So you have to correct for these effects. So it could be that you send 2 photons, but then one of them got lost. And this would also influence the probabilities. But the experimentalists, they know how to correct for these effects. And yeah, so in a way, you're correcting for loss and this G2 by some sort of post-processing of the data.
Okay, but I assume that this is something that works well because the interferometer is so small, right?
Yeah, yeah.
Okay.
Yeah, and for things like 7 photon, even like 5, 6 photons is already a bit tricky to do this experiment because the rates at the moment they're still quite low. The rate of all the photons making it through the experiment, and this is one of the reasons why, for example, the effects of the 7 photon multi-bunching they're still quite hard to access. But people are working on making the chips less lossy. Also, if you
Sure. Yeah.
have photon number resolution detectors, which exist but they're quite expensive, you can use smaller chips. So here you don't need like this demultiplexing step. So and of course, the shorter the depth of the chip, the less the loss is, right? And yeah, but indeed it's challenging at the experimental level.
So there is a related question in the chat. Sorry, thanks first of all for the answer. I will read the question out loud. With a standard 2x2 Hong-Ou-Mandel experiment, if you have a lossy beam splitter, it is possible to tune the bunching into anti-bunching, etc. Can you translate the non-unitary lossy 2x2 beam splitter phenomena to a unitary 3x3 with the third channel acting as the loss or gain? So the question is basically whether you can put all the loss and gain into a third mode and then consider the whole system as unitary.
Yeah, in principle, yeah, you can always model loss by adding extra beam splitters and extra modes with vacuum. So loss is, in a way, is just a beam splitter with vacuum, right? But I'm not sure I understood the full question. So because as I was saying here, we're sort of both selecting on events where there was no loss. So because yeah, we just post-select the data where all the photons made it through. So I don't know if I understood the question. Maybe I would have to read it again, but I don't see how to read the chat. Do I have access to the chat? Maybe.
Yeah, probably when you're
Okay.
not at full screen, it should work. Yeah.
Yeah, so I don't fully understand this question of turning bunching to anti-bunching. I guess, does it mean that maybe the event of when 2 photons made it through to a single mode, when there's loss, sometimes it can look like an anti-bunching event? Yeah, I'm not fully sure I understand. Can you translate the non-unitary lossy 2x2 splitter to a 3x3? Yeah, so I think the last question is a yes. So if you have a 2x2 beam splitter and with loss, yeah, you can always replace it by I think a 3 or probably a 4 mode beam splitter if you don't have a
Sorry to
uniform
interrupt.
loss.
Sorry to interrupt, but indeed, I think you would need possibly 4 modes. I don't see why 3 modes would be enough.
Yeah, I think it'd be a 4 mode beam splitter where 2 inputs with vacuum. Yeah, so I would say yeah, the answer of the second question is yes.
You can just reduce it under strong constraints, right? When you know that the loss is the same in all paths and so on, then maybe you can reduce it, but in general not, right?
Yeah, maybe under some extra exemptions.
Okay. So I consider this as an answer to this question. If not, please shout or write.
I mean, just to come back to the last thing you said, Toby, I don't think that 3 modes would be enough in most of the cases. I think if you have 2 photons occupying 2 modes, and these 2 modes are both, each of them is coupled with an environmental mode, then it's just like if you had 2 virtual beam splitters with environmental mode. But I think you will need 4 modes in total in most cases. I don't actually see when 3 modes would be enough.
I think for fixed configuration of the interferometer, you can probably permute all the losses to a single mode, but I don't think you can do this without knowing the interferometer precisely. I think you cannot do this in a device-independent way, right? But maybe I'm also wrong. Like I don't know. Maybe I'm also wrong. Okay, do we have further questions for Leonardo? Okay. If this is not the case, yes,
sorry,
please, please.
I was just curious. So when you considered the balanced Twitter example, right, and then you said that there is an opposite dependence in the phase for the 3-0. If you compare the 3-0-0 type of terms to the 2-1-0 terms, right? In one case you have a plus cosine, and the other you have a minus cosine.
Actually, the bunching includes both the 300 type and the 210 type.
Okay.
That's why it's even more surprising, because it includes these ones too. So it's sort of a bigger set, but they still have this opposite dependence.
So my question is just, is there any physical interpretation to the fact that it goes in the opposite way, precisely opposite?
It's not very clear. I mean, in a way, I guess it's associated to the suppressions, because okay, I mean these are, but it's like a balance between the when you analyze this probability, there's sort of two opposite contributions, right? There's the fact that when I increase that I somehow want to maximize full bunching, because full bunching is also a part of bunching events, but I also want to get rid of the suppressions from the suppression laws, right?
Yes.
So there's a balance of these two effects. So when I add partial distinguishability, I'm going to decrease these probabilities, but I'm going to increase these ones. And it turns out that they compensate in a way that it's better to have a phase of pi here. But I don't have a very strong intuition.
And perhaps there is a reason might be that there are not so many possible outcomes. I mean, the last type of outcomes would be 1-1-1.
Yeah.
I don't know how does 1-1-1 depend on the phase. I mean, it might simply not depend on the phase. I don't know.
No, it will just be 1 minus this, I think, right? Because
Really?
it's the only extra event. Yeah, because you have 3 photons in 3 modes. So
right.
so 1 minus this would be the permanent. Yeah, it might be a better way to
True.
to explain. 1 minus this would be the permanent of the. Well, it's not really a permanent, right? It would be this tensor permanent, which is a bit more complicated.
So I mean, it makes sense that the complementary probability for complementary event would of course go in opposite direction. Right, so bunching is not fully dual to full bunching, but it's partly, right? Indeed, there is the 1-1-1 component which is out of the story, but
yeah. So what you want to do somehow, if you want to maximize bunching, is to minimize this 1-1-1 component.
Yeah.
Yeah, it turns out, but I don't have a good intuition for this. It might also be some sort of phase compensation between the structure of the treater and because actually the state that realizes this is also the star-shaped state in the in the equator of the Bloch sphere. So it's a little bit similar to the things we had before for 5 photons in the equator of the Bloch sphere. So now we have 3 photons in the equator of the Bloch sphere going to the treater, and this is the one that maximizes bunching actually. So this one here that leads to this Bargman invariant with a phase of pi. So there's probably this compensation happening.
Okay. Thanks.
Okay. Then let's thank our 2 speakers again. Thanks a lot for taking the time. And qmeets already returns next week, actually, with the last 2 talks of this year on quantum simulation with Rydberg atoms. I will send the invitation very soon. And I wish you a beautiful evening. Thanks a lot, guys.
Thank you, Toby.
Much, Toby.
Thank you, everyone.
Bye-bye.
Bye-bye.
Bye.